We're taking a little parenthesis, just a little break from Lesson 4.2 to cover a few topics that are going to be needed before we go back to Lesson 4.2 and talk about the binomial theorem. So the book just assumes that you have certain knowledge before they start covering the binomial theorem. But this little lesson, it's in the Chapter 0 section of your book. This will be helpful to lay some groundwork before we actually discuss the binomial theorem tomorrow. So hopefully you have your calculator ready, and I'm going to be basing everything on the calculator that I have in my room, the TI-30X2S. So if we all use the same calculator, then that'll make this go faster as we look for options. You need to know how to find certain things in this calculator. Okay, so let's just get started with an example or two, like the first 4 problems of the assignment. And this is going to involve what is known as the fundamental counting principle. And I've given you part of the definition there, and let's just go ahead and fill in the blanks. This principle says the number of possible outcomes, fill in that blank, in a sample space can be found by multiplying the number of possible outcomes for each event. Okay, and what is known as an event, you can think of types of certain objects. Each of the different types that are represented in a problem, types of an object will represent, in this case, an event. So let me show you how this applies to one of our word problems. So we have this bike manufacturer, and he makes 2 different types of speed bikes. He makes a 21 speed and a 24 speed. He also makes these bikes in 7 different colors and in 4 different frame sizes. So the question we're supposed to answer is, how many different bikes does the manufacturer make? And so applying the fundamental counting principle, we would first write down the different types of bicycles that are being made, and there's really 3 types. There's bikes made based on the number of gears, and there are 2 different types. There are bikes made based on the number of color options, and you're told that there are 7 different colors to choose from. And there are frame options. In the problem it says there are 4 different frame sizes. So we take each of these types, the total number of bikes within each category, if you will, types, and then we just multiply these together. So 2 times 7 times 4 equals 56. So there are a total of 56 different bikes that this particular manufacturer makes. And that's all based on the fundamental counting principle. So there's another example on the next slide at the very top. This time it's a t-shirt manufacturer. He makes red and gray shirts. So right away there are 2 color options. And he makes these shirts in 6 different sizes. So there are 6 size options. So according to the fundamental counting principle, we just take the number of shirts within each type and simply multiply 2 times 6, and that gives us our answer of 12. Okay, and that's the same type of thing that you're going to be doing on the first 4 problems of your assignment. Okay, so let's go now to another topic. Roman numeral 2 is a discussion of this concept called permutations. I want you to be very familiar with what we mean by permutations. So my definition that we'll fill in, these are also counting problems, but they're based on their whole emphasis for permutations is how many different ways can people or objects be arranged, and how many different orders can we come up with either people or objects. So we'll go ahead and fill in the technical definition. Counting problems can also involve determining the number of different arrangements of objects, or you could also say people. An arrangement of a group of distinct objects in a certain order is called a permutation. Okay, so the thing to take away from permutations, because you do need to make a distinction between permutations and what we're going to talk about in just a few minutes, combinations. A lot of students have a difficulty reading a problem and understanding which one they're dealing with. So permutations are all about order, arrangements. Down here at the bottom of the slide, I've given you some keywords. These keywords don't always show up, but these are words to look for to give you a clue that the problem you're dealing with represents a permutation. Words like arrange or arrangements, sequence, order, rank or ranking, lineups, etc. Words like that. And if these words aren't used, then it's implied based on the context of the problem. So let me show you an example of a permutation problem, just a real basic one. In this example 1, we want to know in how many different ways can 6 students be lined up for a group picture. Well, I'm going to draw blanks here to represent the positioning of the 6 different students. Okay, so let's just think about this for a second. In this spot, there's a possibility that 6 different students can occupy this first location. So I'm going to put the number 6 here to represent we have 6 possibilities. Well, after that, for this second spot, obviously if one student occupies this, then we've got 5 students that could occupy this second location. And then if we move on down, since these 2 are occupied, we're left with 4 students who can fill this position. And then you can see the pattern. That leaves us with 3 students possible to fill this location, 2 for this one, and 1 for this one. So the way I'm going to get my answer is I'm going to multiply these together. So remember, it's the fundamental counting principle. And basically, if you take your calculator and multiply all of these together, 6 times 5 times 4, all the way down to 1, you should get 720. There are 720 different ways that we could arrange these 6 students. Well, what we just did is an example of a number. Here it's just indicated as n, and then you see the exclamation point that follows. And in a math context, this exclamation point reads as factorial. So this represents a number n factorial. And what that means for us is, here's another example separate from this. If I ever ask you to give me 8 factorial, well, you're thinking you start with 8 and then you just multiply, then by 7, by 6, by 5, all the way. You just keep on multiplying until you get down to 1. So 8 factorial, this is the expanded form, and this is the actual result of that. So in our problem, what we ended up doing was 6 factorial, which you can see is 6 times 5 times 4 times 3 times 2 times 1. And that equals 720. Well, let me show you how you can do this real fast, because sometimes we have large numbers. You might have 15 factorial, and you obviously don't want to list out all of these numbers and multiply them together. So if you've got your calculator, let's just go ahead and do this 6 factorial problem with a calculator. So go ahead and key the 6. And then on your calculator, it's near the top. If you go to the second row, you're looking for a button that says PRB. It's the abbreviation for probability. Okay, so go ahead and press the PRB button, and when you're doing permutations and combinations, this button is used a lot. If you notice, once you press PRB, you've got 3 options, and we're going to talk about all 3 eventually. But I want you to arrow over to where you see you're going to hit the arrow button twice, and you'll highlight the factorial option. Okay, and then hit enter. And now on your screen, after you hit enter, you should see 6 factorial displayed, and you'll just need to hit enter again, and you see it gives you the number 720. Okay, so before we leave this example, let me just make this hopefully pretty clear. Whenever you're asked to do the arranging of all of the items that you're given, notice there are 6 students, and we want to find out the arrangements of all 6. How many different ways can all 6 be arranged? Then you can very simply just take the number of students or people, objects, whatever the case is, and do that number factorial, and you've got your answer. But that's only if all of the people or objects are being arranged. All of the people that you have available are being arranged. All right, so let's take a look at another example. Example 2, we got 9 players in a baseball lineup, so we only have 9 available. No 2 players can share the same spot. How many different lineups are possible? Well, it's very similar to our previous problem because we are arranging all 9. Okay, I'm not arranging part of the group, I'm arranging the whole group. So to get my answer, I'm going to do simply 9 factorial. So once again, I'm going to clear my previous answer. I'm going to key the 9 and press PRB, arrow over to factorial, hit enter, enter again, and hopefully on your calculator you're seeing 362,880. Okay, so that is an example of a permutation problem where we're interested in arranging or putting in order all of the elements that we have available. Well, let's take a look at a different example, still a permutation, but notice the difference. Example 3 says we have 7 yachts in a race, and we're going to give prizes to first, second, and third. How many arrangements, there's a key word telling me that this is a permutation, how many arrangements of first, second, and third are possible? So this is not arranging all 7 yachts. We have 7 available, but we're only arranging 3 at a time, first, second, and third places. So this is going to be handled a little bit differently. Whenever we're interested in arranging part of the entire group, only a certain number at a time of the entire group, then we're going to use a formula that I've provided for you at the bottom of the screen. N stands for the number of, in this case, the total number of objects that we have to choose from, in this case, 7 yachts. And R will represent how many we're wanting to arrange at a time. So plugging into this formula, N being 7, it's 7 factorial, and then the denominator will be 7 minus 3, which is 4 factorial. Okay? And so now you can just grab your calculator and you can actually just do it exactly like it shows. You might want to clear the previous answer. So I'm pressing 7, PRB, and then choose factorial. I see 7 factorial on my screen. And now I'm going to do divided, and then I'm going to do the same thing for 4 factorial. Okay, so on my display right now, I see 7 factorial divided by 4 factorial, and I press enter, and I get 210. Well, that is one way of doing it using this formula. And I want you to be somewhat familiar with the formula, but the calculator really does this work for us. If we can recognize that we're dealing with a permutation, then these are really pretty easy problems to do with the calculator. So let me show you another way of coming up with the answer 210. All right, clear your calculator, and we're going to key in this first number, this total number of objects that we have to choose from. So you can go and key in 7. And now I want you to press PRB again, and this time we're going to choose the NPR option. It stands for permutation of a certain number of objects, but only a certain number at a time. Okay, so NPR should be highlighted, so press enter. And now following that, you can see on your screen right now it says 7 NPR, and key in the 3 and press enter. And hopefully you notice that we got the same answer that we got before where we used the formula. Okay, so I want you to know where that is. That's very handy. Again, the challenge for most people is just understanding, am I working with a permutation or am I working with a combination? And hopefully we'll make that really clear by the time this lesson is over. So let's do one more of these. Here's example 4. This photographer has a total of 15 photographs, and he's wanting to select 10 for a gallery show. So let's see if we can pick up on a key word. How many ways can the photographer arrange? All right, that's a key word to tell us this is a permutation. And so in my calculator, I'm going to get my answer like this. I got 15 photographs to choose from, and I'm only arranging 10 at a time. Okay, so we'll clear our calculator. 15, PRB, NPR, 10. And this is one of those cases where your answer is pretty large, and it's so large that your calculator can't display the entire number. It's given it to you in scientific notation. And so I'm okay with you. You can just round, as I've done here, to the third decimal place, and then just show what your calculator shows. So I'm okay with you showing these really big numbers in scientific notation form. All right, and so that's an example of permutations. So we've looked at the fundamental counting principle, we've looked at permutations, and now let's go to combinations. Combinations are completely different. We do not care how the items are being arranged or ordered. Notice, order does not matter. The order is irrelevant. We basically just want to see how many small groups we can make up out of a big group. So let me show you an example. Here we have this restaurant that offers a total of 8 side dishes. How many different ways can a customer choose 3? Well, the order of side dishes really doesn't matter. We just want to know how many different 3 side dish groups can we come up with out of a total of 8 options. Well, here's the formula for combinations. Notice it's a little bit different than the permutations. It's different just by the way the denominator is represented. So I'm going to do the same thing. I'll just show using the formula. We have 8. N is always the bigger number. I've got 8 side dishes to choose from, but I'm only picking 3 at a time, so R is actually 3. Okay, so using the formula, I would have 8 factorial divided by 3 factorial times 5 factorial. 8 minus 3 is 5. Okay, and so you can use your calculator here as well, but you need to use parentheses in the denominator. So let me walk you through this. You can go ahead and do 8 factorial and just leave it there. Don't hit enter yet. You can just leave 8 factorial and then divided by. Now the 3 factorial, 5 factorial needs to be put in parentheses. So I did left parentheses, 3 factorial, and then right beside that, I'm going to do 5 factorial. I don't have to put anything between them, but the entire denominator needs to be in parentheses. All right, so I just closed my parentheses, and the answer that I got is 56. Okay, well, let's do it using the NPR option. That's the formula. So using NPR like we did in NCR like we did in PR, you would do 8 and then PRB, choose this time NCR, C stands for combination, and it's the same process that we use with permutations, just different choice. Key in 3, and hopefully you were able to also get 56 using NCR. Okay, so everything you need pertaining to fundamental counting principle, permutations, combinations is found under that PRB button on your calculator. Okay, let's do another example. This one actually should have been number 1, and here's number 2. So how many ways are there to choose 5 cards from a standard deck of 52 playing cards? Well, I got 52 to choose from, and this is a combination because order is not implied. Nothing about how are they arranged, how many different orders can I come up with. It's a combination. So in your calculator, we'll clear what we had before. 52, PRB, choose NCR, then choose or key in 5, and you should have 2,598,960. Okay, there are that many 5-card groups that we can come up with out of a total standard deck of 52 playing cards. Okay, so part 4, some of your homework will be giving you a statement, and your job is to determine, does this represent a permutation or a combination? And then once you've made that decision, go ahead and find the number. Okay, so example 1 says, what if we wanted to make a playlist of 5 songs from a total of 12 songs? Well, order is not implied, nothing about the songs have to be arranged in a certain way, so this is a combination. So that'll be answer part 1, and then answer part 2, I'm going to use my calculator to actually find the result. So in my calculator, I'm going to do 12 NCR 5, 12 PRB NCR 5, and I got 792 as my answer. Okay, number 2. We have 15 students who asked to visit the admissions representative from a college. Each visit includes 1 student. In how many ways can 10 time slots be arranged or be assigned? Well, none of our key words for permutations are present in this problem, but since we're talking about time slots, that implies that order matters. I mean, we're going to have someone to come in first, maybe at 10 o'clock, and then someone comes in second, maybe at 10:30. So once again, sometimes you're going to have to read between the lines and ask yourself, is this an arrangement of people or objects, or is it merely choosing a certain number out of a big group? And this is definitely going to be an arrangement because we're talking about time slots. So in your calculator, you can do 15 in PR, and then we have 10 students being arranged at a time. And we came up with this actually in example number 4, so that is your answer again. Okay, example number 3. I want to hang 6 pictures in a row, that's a clue, on a wall. You have 11 pictures to choose from. How many here's a big clue, how many picture arrangements are possible? So when you see arrangements, orders, lineups, that kind of thing, that's a clue that you're dealing with a permutation. How many different arrangements can we have? And so we start with 11 pictures to choose from in PR, and we're only arranging 6 at a time. So grab your calculator, clear it, 11, PRB, NPR, and 6, and that's 332,640. Example 4. How many different teams of 11 players can be chosen from a soccer squad of 16? Well, nothing is talked about order. How many different ways can the players be arranged? We just want to know how many different 11-player groups can we come up with out of a total of 16 players. So this is a combination. And so I've got 16 to choose from in CR, and I'm going to choose 11, groups of 11. So clear your calculator, 16, PRB, NCR, 11, and this is 4,368. 4,368 different 11-player groups can be formed out of a squad of 16. Number 5, how many different 4-letter codes can be made if no letter can be used twice? Okay, well, think about how many letters we have in the alphabet. There's 26. And again, I don't see any key words here like arrangements or orders, but if we're talking about a code, it's very important for codes that the letters have to be keyed in a certain way, in a certain order, or the code won't work. So this is implied that this has to be a permutation. Order definitely matters when it comes to codes. All right, so I've got 26 total letters to choose from in my alphabet. I'm going to go do NPR, but I'm only arranging 4 at a time. Okay, so grab your calculator again, clear it, 26, PRB, NPR, and this time you're going to put in 4, and that's 358,800. That many different 4-letter codes can be made if no letter can be used twice. Okay, and then to help you out just a little bit for this very last problem, first of all, this assignment is found on page P12. It's going back to the chapter 0. And find page P12 either in your book or your online textbook. And I just want to kind of set you up with number 19, the very last problem in the assignment. Okay, so let's take a look. I don't want to do the whole thing. I want to just kind of open it up for you a little bit and then see what you can come up with for the rest. Well, Abby is registering at a website and she must select a 6-character password. And then we're told the password can contain either letters or digits. Okay, so answer A, really it's a 2-part answer. Let's answer the first question first. How many passwords are possible if characters can be repeated? Well, first of all, let's think about how many characters we have to work with. We have the whole alphabet, which is 26 letters, of course. And then it uses the word, it says it can use either letters or digits. Well, there are 10 digits, 0 through 9. So that makes a total of 36 possibilities for characters. So let me just kind of set it up this way. Here are the blanks representing my 6 characters for the password. Okay, sort of like we did early on when we were talking about 6 students being lined up for a picture, but there's many, many more possibilities here because in this first spot, since I have a total of 36 characters at my disposal, any letter or any number could be put here. So there are 36 possibilities for this first spot in the password. The second spot in the password, the second item of the password, since we're told that characters can be repeated, well, that means there's also 36 characters available for the second item in the password. And that's true again for the third, and for the fourth, and for the fifth. You notice that since the characters can be repeated, then they're all available for every single position in the password. So kind of work this one for you. You can see that your answer really is going to be 36 to the 6th power. And I'll let you go ahead and use your calculator and come up with that. Well, how does it change to answer the second part of letter A? I'm going to go back and here's my password. How does it change things the way it's worded if it says no characters can be repeated? Well, that means in the first character of your password, there's 36 choices. But if I can't repeat, that means I've only got 35 choices here. And that means I've only got 34 here, 33 here, 32 here, 31 here. Okay, so you get the gist of that problem. I'll let you go ahead and finish that. Okay, letter B, kind of similar, the first part anyway. How many passwords are possible if all characters are letters, just letters that can be repeated? Well, I think you can probably work this one out yourself based on our answer for letter A. For letter B, now you only have letters at your disposal. So go ahead and finish that one off. Think about what we did for letter A up above. Okay, so let's look at the second question of letter B. If the password must contain exactly one digit. Okay, so we're still, characters can be repeated, letters can be repeated, but we also have to have one digit involved. All right, so let's think about this for a second. Let's just imagine that we let our one digit be here in this first spot, the first character of our password. So I got 10 choices. And then the rest of these are just letters, and they can be repeated. So I got 26 choices for the second character, 26 again for the third, 26 for the fourth, 26 for the fifth, and so forth. Okay, well that's one password where the first character of the password is a digit. What if the second character of the password is a digit? Okay, I'll try to get you thinking a little bit, and then I'm going to let you take it from there. And then what about if the third digit or third character of the password is a digit and all the others are letters? And then what about the fourth, and what about the fifth, and then the sixth? What if it was only the sixth character being a digit? Okay, so I'm going to see if just seeing this much of letter B, if you can go ahead and finish it and come up with an answer. It's okay to be wrong, and bring your answer to class, and we'll see what you came up with, and we'll talk about it a little bit more. All right, so that's your assignment, and once we go through this, we talk about it, then we're ready to go back to lesson 4.2 and talk about the binomial theorem. If you have any questions, let me know.